When Richard Feynman spoke about force, he deliberately challenged one of the most comfortable habits of the human mind, the desire to treat ideas as if they were tangible objects. From childhood, we learn to imagine forces as pushes and pulls, almost like invisible hands acting on matter. This picture is useful at a basic level, but Feynman insisted that it quietly misleads us. In the physicist's way of thinking, force is not a physical thing hiding inside nature. It is a concept, a mathematical tool created to summarize patterns in motion and to allow us to predict what will happen next. The moment we forget this and begin to think of force as a substance, we step away from understanding and move toward comforting illusion. To see why this distinction matters, it helps to consider what physics is trying to achieve. Physics does not aim to explain nature in the sense of telling a story that feels emotionally satisfying or intuitively obvious. Its real goal is far more modest and far more powerful: to describe regularity in the world so accurately that we can predict outcomes of experiments. When physicists talk about force, they are not claiming they have discovered a hidden engine of motion. They are saying that certain changes in motion reliably occur together with certain conditions, and that it is convenient to summarize this relationship with a single word and a precise equation. Feynman often emphasized that when we observe an object accelerating, we introduce the idea of force to account for that acceleration. But the force itself is not observed in the same way we observe position or time. We never directly see a force, we infer it from motion. This alone should make us cautious. If something is never directly measured but only calculated from other quantities, it may be wiser to treat it as a bookkeeping device rather than as a physical entity. Force, in this view, is part of our description of nature, not necessarily a separate ingredient of nature itself. This way of thinking becomes clearer when we examine Newton's second law. In everyday teaching, it is often phrased as a force causes acceleration. The language suggests causality, as if force were the agent and acceleration the result. But mathematically, the law simply relates acceleration to force through mass. If we rearrange the equation, acceleration defines force just as much as force defines acceleration. There is no privileged direction of explanation. The equation works both ways. Feynman pointed out that the law does not explain why objects accelerate, it merely states how acceleration is related to the quantities we choose to call forces. The predictive power of this approach is what gives it value. Suppose we observe that whenever an object is placed near Earth's surface, its motion changes in a consistent way. Instead of memorizing countless individual observations, we invent the idea of a gravitational force and assign it a numerical value. With that single concept, we can predict how fast an object will fall, how far it will travel in a given time, and how different masses behave under the same conditions. The force is not something we detect independently. It is a summary that allows us to compress a vast amount of experimental data into a compact rule. Feynman was careful to stress that this does not make force unreal in a practical sense. Concepts can be extremely useful even if they are not physical objects. Money, for example, is not a force of nature, but it powerfully organizes human behavior because it summarizes agreements and expectations. In the same way, force organizes our understanding of motion. The danger lies not in using the concept, but in forgetting what kind of thing it is. Once we start asking questions like what is force made of, or where exactly is the force located, we are treating an abstract tool as if it were a material object, and physics quickly becomes confused. Another reason Feynman resisted the idea force as a thing is that history shows how easily such ideas are replaced. In earlier centuries, scientists believed in substances like phlogiston to explain combustion or caloric fluid to explain heat. These concepts worked for a time, allowing predictions within limited domains, but they were later abandoned when deeper theories emerged. Force itself has undergone similar transformation. In modern physics, many phenomena once described entirely in terms of force are now more naturally described using fields, energy, and momentum. The success of these newer descriptions suggests that force was never a fundamental substance, but a convenient stage in the evolution of our understanding. This perspective also helps resolve a common philosophical frustration. People often ask what really causes motion, expecting an ultimate answer. Feynman's approach gently dissolves the question. Physics does not provide ultimate causes in the metaphysical sense, it provides reliable relationships. When we say a force is present, we are not revealing nature's deepest secret. We are labeling a pattern that has proven stable across countless experiments. The satisfaction of physics lies not in final explanations, but in the astonishing effectiveness of these patterns. There is also a subtle psychological benefit to this view. When force is treated as a thing, students often struggle to imagine how it works in unfamiliar situations. They look for mental pictures that resemble everyday pushes and pulls, and when those pictures fail, confusion follows. By contrast, when force is understood as a predictive tool, the emphasis shifts to calculation and consistency. The question becomes not what does the force look like, but what does the equation predict and does the experiment agree? This mindset is closer to how physicists actually work. Feynman frequently warned that human intuition is shaped by limited experience. We are comfortable with solid objects touching each other but uneasy with invisible interactions. By accepting force as an abstract construct, we free ourselves from the need to visualize everything mechanically. We allow mathematics to guide us where intuition cannot. In doing so, we gain access to domains far removed from everyday life, such as atomic scales and cosmic distances, where common sense is no longer a reliable guide. At a deeper level, this keynote reflects a broader theme in Feynman's philosophy of science: humility before nature. He insisted that our concepts are provisional. They work because they work, not because they satisfy our desire for simple stories. Force is powerful because it predicts motion with extraordinary precision, not because it feels intuitively real. If tomorrow a better concept replaced force entirely, physics would accept the change without regret, just as it accepted the replacement of older ideas in the past. Understanding force the physicist's way, then, means letting go of the need to reify our tools. It means recognizing that physics progresses by inventing concepts that organize experience, testing them relentlessly, and discarding or refining them when they fail. Force, seen in this light, is not diminished by being a predictive tool. On the contrary, its greatness lies precisely in its ability to connect observation and prediction so elegantly. It reminds us that the true power of science is not in claiming to know what reality is at its core, but in learning how to speak about reality in ways that allow us to foresee its behavior with remarkable accuracy. In continuing this idea, it is important to recognize how radically different the physicist's use of force is from everyday language. In ordinary speech, we say, "We use force," as if it were something stored in our muscles and released at will. This language is practical for daily life, but it quietly smuggles in the idea that force is a kind of substance. Feynman argued that physics deliberately strips away this everyday meaning and replaces it with something more disciplined. In physics, force does not belong to an object the way color or mass does. It appears only when we compare how motion changes from one situation to another. This distinction becomes especially clear when we examine situations where the same motion can be described without mentioning force at all. Consider an object moving at constant velocity in empty space. According to Newtonian language, there is no net force acting on it, but nothing physically changes in the object. At the moment we decide to say the force is zero, the object simply continues moving. The absence of force is not something we detect. It is a conclusion we draw from the motion. This reinforces Feynman's point that force is inferred, not observed, and that it enters our description only when it is useful for prediction. Feynman often illustrated this with a deeper question: what would the universe look like if we never invented the concept of force? Surprisingly, much of physics could still be done. We could describe motion directly in terms of how positions change with time and how those changes depend on conditions. Force simply provides a compact way of organizing these descriptions. It is a shortcut, not a necessity imposed by nature. Nature does what it does regardless of the words or equations we choose to describe it. This idea becomes even more powerful when we move beyond classical mechanics. In modern physics, especially in quantum mechanics and relativity, force becomes less central. In quantum theory, particles do not always move along well-defined paths, making the traditional idea of force harder to apply. Instead, physicists calculate probabilities, energies, and interactions using mathematical frameworks where force appears only indirectly, if at all. The success of these theories shows that force was never the final word, but a stepping stone toward deeper descriptions. Feynman was particularly fond of pointing out that, even when force remains in our equations, its interpretation changes. In classical mechanics, force is linked directly to acceleration. In quantum field theory, what we call forces emerge from the exchange of particles or from the structure of fields. The word force remains, but its meaning shifts. This flexibility would be impossible if force were a literal physical object. It is possible precisely because force is a conceptual tool, adaptable to new contexts as our understanding grows. Another important aspect of this keynote is the role of measurement. Physics relies on quantities that can be measured and compared. Position, time, mass, and energy have clear experimental definitions. Force, by contrast, is usually defined through its effects. We measure force by observing how a spring stretches or how an object accelerates. The measuring device itself relies on motion or deformation, which again shows that force is not primary. It is a name we give to a pattern in measurable changes. This realization also helps clarify why debates about the true nature of force often lead nowhere. Asking what force really is, beyond its mathematical definition and experimental consequences, is like asking what a coordinate system really is. A coordinate system is not part of nature. It is a human invention that helps us describe nature. Yet it can be extraordinarily powerful. Force occupies a similar status. It is not a fiction, but it is not a substance either. It is a structured way of talking about how motion behaves. Feynman's insistence on this point was not philosophical hair-splitting. It had practical consequences for how physics is taught and understood. When students imagine force as something tangible, they often make systematic errors. They might think an object in motion must have a force pushing it forward, or that removing a force will cause motion to stop. These misconceptions disappear once force is understood as a description of changes in motion, not as a cause that must always be present. The object moves because that is what objects do unless their motion changes. Force is simply our label for the circumstances under which it does change. This way of thinking also prepares the mind for more advanced ideas. In Einstein's theory of relativity, gravity is no longer treated as a force in the traditional sense. Objects follow curved paths in space-time, and what we interpret as gravitational force is a manifestation of geometry. From Feynman's perspective, this is not shocking. If force was always a predictive tool, there is no problem with replacing it by a different tool when it proves more effective. The success of relativity becomes a confirmation of the original insight. Our concepts are chosen for usefulness, not because they mirror reality in some absolute way. There is also a deeper philosophical lesson here about explanation itself. Humans crave explanations that feel complete, final, and intuitive. Feynman repeatedly warned that nature does not owe us such satisfaction. Theories succeed not because they feel right, but because they work. Force works within a certain domain, with extraordinary precision. Beyond that domain, new ideas take over. Understanding force the physicist's way means accepting the explanation in science is always conditional and always subject to revision. This attitude fosters intellectual honesty. Instead of pretending we have uncovered ultimate causes, we admit the limits of our knowledge. We say, within this framework, this is how things behave. That statement is modest, but it is also incredibly powerful. It allows physics to progress without being trapped by its own concepts. Force can be used, modified, or abandoned as evidence demands, without any sense of betrayal. In the end, the idea of force as a predictive tool reflects the true spirit of physics that Feynman championed. Physics is not a catalog of invisible mechanisms, but a living process of building models that connect experience to prediction. Force is one of the most successful models ever invented, not because it tells us what reality ultimately is, but because it lets us calculate what reality will do. To understand force in this way is to step closer to the physicist's mindset, curious, precise, skeptical of comforting pictures, and always guided by experiment rather than intuition. When Richard Feynman discussed Newton's laws, he repeatedly tried to rescue them from a misunderstanding that has followed them for centuries. In textbooks and popular explanations, Newton's laws are often presented as if they explain why things happen. A force causes acceleration. An object in motion stays in motion unless acted upon. Action produces an equal and opposite reaction. These statements sound causal, almost philosophical, as though they reveal the hidden machinery behind motion. Feynman insisted that this reading is deeply misleading. Newton's laws do not tell us why nature behaves as it does. They tell us how certain quantities are related, and nothing more. Their greatness lies not in causal storytelling, but in their precision as relationships that allow prediction. To understand this properly, one must first step back from everyday language. In daily life, cause and effect feel obvious. We push a door, and it opens. We throw a ball, and it moves. Our minds are trained to think in terms of agents and results. When this habit is imported into physics, force becomes an agent and acceleration becomes the result. But Newton's second law, written mathematically, does not contain this notion of agency. It simply states a proportionality between quantities. Acceleration, force, and mass are linked in a fixed way. The equation does not privilege one as the cause and the other as the effect. It merely states that they vary together. Feynman often emphasized that the direction of explanation is something we impose, not something demanded by nature. We say force causes acceleration because it matches our intuition of pushing and pulling. But mathematically, we could just as easily say acceleration defines force. In fact, that is often how force is determined in practice. We observe how an object accelerates and calculate the force from that motion. This alone should undermine the idea that Newton's laws reveal a deeper causal mechanism. They are rules for calculation, not metaphysical declaration. This becomes clearer when we consider how Newton's first law is usually misunderstood. It is often taught as if it explains why objects keep moving, because no force acts on them. But this explanation is circular. We define no net force precisely as the condition under which motion does not change. The law does not explain persistence of motion, it codifies it. Feynman pointed out that the law is really a definition of inertial motion and inertial frames. It tells us how to identify situations where Newton's other laws apply cleanly. It is not a statement about causes hidden inside objects. The same is true of the third law. Action and reaction are equal and opposite. Not because nature is fair or balanced in a moral sense, but because experiments show that momentum is conserved in interactions. The third law summarizes this regularity in a compact way. It does not explain why momentum is conserved. It simply reflects the fact that it is. Later physics would show that conservation laws arise from deep symmetries of nature, but even those deeper explanations are still relational, not causal in the everyday sense. Feynman's insistence on this point was not an attack on Newton. On the contrary, it was a defense of Newton's true achievement. Newton did not claim to explain the ultimate causes of motion. He provided a framework that connected observations with predictions. The laws worked spectacularly well across an enormous range of phenomena, from falling apples to planetary motion. Their success came from their internal consistency and their agreement with experiment, not from their ability to satisfy philosophical curiosity about causes. A crucial consequence of this view is that Newton's laws do not stand alone. They require definitions of quantities like mass and force, and those definitions themselves rely on experimental procedures. Mass, for example, is not an inherent label stamped onto an object by nature. It is defined operationally through how objects accelerate relative to one another under the same conditions. Force, in turn, is defined through its relation to acceleration. The laws form a tightly interwoven system of relationships. Trying to isolate one element as the ultimate cause misunderstands the structure of the theory. Feynman liked to point out that this relational structure is what makes physics robust. Because the laws are not tied to a particular story about causes, they can survive reinterpretation. When Einstein reformulated gravity, Newton's law of gravitation was no longer seen as a force acting at a distance. Instead, it became an approximation to a deeper geometric description of spacetime. Yet Newton's equations remained useful within their domain. This would not have been possible if they had been tied to a specific causal picture of gravity as a literal pull through empty space. Another way to see this is to consider how different coordinate systems affect our description of motion. In one frame, an object may appear to accelerate, In another, it may not. We then introduce fictitious forces to preserve Newton's laws in non-inertial frames. These forces are not real in the sense of being caused by physical interactions. They arise from our choice of description. This fact alone reveals that force, as used in Newton's laws, cannot always be a cause in the usual sense. Sometimes, it is simply a mathematical artifact introduced to maintain relational consistency. Feynman used such examples to train the mind away from naive realism about physical concepts. He wanted students to see that physics is not about naming causes, but about discovering patterns that remain invariant under careful measurement. Newton's laws express such invariance. They tell us that certain relationships hold across a wide range of circumstances. Whether we interpret those relationships causally is a matter of taste, not necessity. This perspective also dissolves many common confusions. Students often ask what really causes acceleration. Is it force? Is it energy? Is it momentum transfer? From Feynman's point of view, this question has no single correct answer. Each concept belongs to a different but equivalent framework for describing the same phenomena. Newton's laws express one framework. Energy-based formulations express another. Lagrangian and Hamiltonian mechanics express still others. None of these frameworks owns the truth. They are different relational languages describing the same underlying regularities. The documentary-style clarity of Feynman's thinking shines here. He stripped away the illusion that physics must explain everything in a cause-and-effect narrative that matches human intuition. Instead, he showed that the power of Newton's laws lies in their restraint. They do not claim more than they can deliver. They say, if these conditions hold, motion will behave in this way. That is all. And that is enough to build bridges, launch spacecraft, and understand the motions of stars. By seeing Newton's laws as relationships rather than causes, we also gain a deeper appreciation for their limits. They work extraordinarily well at ordinary speeds and scales, but they fail at relativistic speeds and quantum scales. When they fail, we do not accuse nature of disobedience. We recognize that the relational framework is incomplete. New relationships are needed. This attitude is only possible if we never believed the laws were ultimate causes in the first place. In this way, Feynman's interpretation protects physics from dogmatism. Laws are not commandments imposed on nature. They are summaries extracted from experience. They are always provisional, always subject to refinement. Newton's laws endured for centuries not because they were treated as sacred truths, but because they continued to work. When deeper theories appeared, they were absorbed as limiting cases. The relational view made this transition smooth rather than catastrophic. Understanding Newton's laws in this way also changes how we think about explanation itself. An explanation in physics is not a story about hidden agents, but a demonstration that a phenomenon fits into a consistent web of relationships. When we explain motion using Newton's laws, we are not revealing a secret cause. We are showing that the motion obeys the same relationships as countless other motions. That recognition brings understanding, not because it satisfies curiosity about causes, but because it reveals unity. This is the heart of the second keynote as Feynman saw it. Newton's laws are among the greatest achievements of human thought, not because they explain why the universe behaves as it does, but because they show how diverse phenomena are connected through simple, precise relationships. To grasp this is to move closer to the physicist's mindset, where understanding means seeing patterns, accepting limits, and valuing predictive power over comforting stories about cause and effect. Continuing this line of thought, it becomes clear why Feynman believed that confusion about Newton's laws often comes from language rather than from mathematics. Words like cause, effect, push, and pull are borrowed from human experience, where intentions and agents matter. Physics, however, deals with impersonal regularity. When Newton wrote his laws, he was not trying to describe an invisible mechanism operating behind the scenes. He was offering a compact mathematical structure that linked measurable quantities. Over time, the language wrapped around these laws hardened into misleading interpretations, and Feynman's task was to peel those layers away. One of the most revealing examples lies in how we talk about mass. In everyday thinking, mass feels like a fixed property, an intrinsic heaviness belonging to an object. Newton's laws seem to suggest that mass resists acceleration and mediates the effect of force. But operationally, mass is defined through relationships. We compare how different objects accelerate under the same conditions and assign numbers that make Newton's equations consistent. There is no deeper explanation of mass within classical mechanics. It is not a cause. It is a parameter in a relationship. Feynman stressed that recognizing this prevents us from asking the wrong questions, such as why mass resists acceleration, when the theory itself never claims to answer that. This relational character becomes even clearer when we consider systems of many particles. In such systems, individual forces between particles can be extraordinarily complex. Yet the overall motion often follows simple rules. The center of mass moves as if all the mass were concentrated at one point, and all external forces acted there. This simplicity is not because the forces inside the system vanish, but because their effects cancel in a precise relational way. Newton's laws allow us to ignore immense internal complexity and focus on a few collective quantities. That power does not come from identifying causes, but from recognizing relationships that remain stable under aggregation. Feynman also highlighted how easily causal language breaks down when we look closely at interactions. Suppose two ice skaters push off from one another. Who caused the motion? Did one skater's force cause the other to move? Or did both move simultaneously due to a mutual interaction? Newton's third law tells us the forces are equal and opposite. There is no privileged cause. The motion of each skater is part of a single interaction described relationally. Any attempt to assign a one-way cause distorts what actually happens. This insight becomes crucial in more abstract contexts. In electromagnetism, charges exert forces on each other, but the forces depend on their motion as well as their position. Changes propagate at finite speeds, and the simple picture of instantaneous cause and effect fails. Newtonian causal language struggles here, while relational equations continue to work. Maxwell's equations do not say that one charge decides to act on another. They describe how electric and magnetic fields evolve and how charges respond to those fields. The structure is relational through and through. Feynman wanted students to feel comfortable with this shift. He argued that discomfort often arises because we expect physics to answer philosophical questions it was never designed to answer. When we ask why force causes acceleration, we are asking for a cause behind a relationship. But physics stops at the relationship itself. It says this is how nature behaves as far as we can tell. If you want a deeper why, you must build a new theory. And that theory will again consist of relationships, not ultimate causes. This way of thinking also explains why different formulations of mechanics can coexist peacefully. Newtonian mechanics uses forces and accelerations. Lagrangian mechanics uses energies and generalized coordinates. Hamiltonian mechanics uses phase space and conserved quantities. Each formulation emphasizes different relationships, yet all produce the same predictions when applied correctly. If Newton's laws were about fundamental causes, such equivalence would be mysterious. Seen as relational frameworks, it becomes natural. They are different maps of the same territory. Feynman often used this equivalence to undermine the idea that one formulation is more real than another. Physicists choose the language that best suits the problem at hand. For planetary motion, Newton's laws may be simplest. For complex constraints, Lagrange's equations may be clearer. For quantum systems, Hamiltonians are essential. Reality does not care which language we use. What matters is internal consistency and agreement with experiment. Another subtle but important point concerns time. In everyday causality, causes precede effects in time. Newton's laws, however, are time-symmetric in their basic form. The equations work equally well forward or backward in time. If force were a cause in the everyday sense, this symmetry would be puzzling. How can a cause work backward? The answer is that force is not a cause in that sense at all. It is part of a mathematical relationship that does not encode a direction of time. The arrow of time enters physics through our considerations, not through Newton's laws themselves. Feynman believed that appreciating this symmetry helps prevent deep misunderstandings. Students sometimes imagine forces as agents pushing motion forward in time. but the equations do not single out the future. They simply connect states at different times. Whether we interpret one state as causing another is a psychological overlay, not a feature of the physics. This perspective also clarifies the role of experiments. Newton's laws were not derived from pure reasoning, they were distilled from observation. Their status is empirical, not logical necessity. They work because nature behaves in a way that fits them, not because they must be true. Feynman emphasized that no amount of philosophical argument can replace experimental testing. A single experiment that contradicts the laws forces revision, regardless of how elegant or intuitive the laws may seem. In this sense, Newton's laws are living tools rather than eternal truths. They survived for centuries because they continued to match observations within their domain. When discrepancies appeared, as in the orbit of Mercury or the behavior of light, new theories emerged. Those theories did not declare Newton wrong in every respect, they showed the limits of the relationships Newton discovered. This layered structure of knowledge is only possible when laws are seen as relational summaries rather than as final causes. Feynman's treatment of Newton's laws therefore carries a broader lesson about scientific understanding. To understand a law is not to imagine a mechanism behind it, but to know how and when to use it. It means knowing what quantities to measure, how to relate them, and what predictions follow. It also means knowing when the law no longer applies. This practical understanding is far more powerful than any metaphysical story about causes. As this second keynote unfolds, it becomes evident that Feynman was training a particular intellectual attitude. He wanted students to resist the temptation of false depth, the feeling that one has explained something simply by naming a cause. True depth in physics comes from recognizing patterns that unify many phenomena, and from accepting that these patterns may not align with everyday intuition. Newton's laws achieve their greatness precisely because they do not overreach. They say exactly what can be said, no more and no less. In the end, seeing Newton's laws as relationships rather than causes frees the mind. It removes unnecessary questions that lead nowhere and focuses attention on what physics does best: prediction, coherence, and testability. It aligns our understanding with the actual practice of science, where equations are judged by their success, not by their ability to tell satisfying stories. This was the spirit Feynman embodied and tried to pass on, a spirit that values clarity over comfort and accuracy over illusion, and that finds beauty not in ultimate causes, but in the elegant web of relationships that nature reveals. When Richard Feynman spoke about interactions and mutual influence, he was trying to correct a deeply rooted habit of thinking that treats motion as a one-sided affair. In everyday life, we imagine one object acting on another as if influence flows in a single direction. A hand pushes a wall, a bat hits a ball, a truck collides with a car. Our language encourages us to identify an actor and a receiver. Physics, however, reveals that this picture is incomplete. In the physicist's view, every force is part of an interaction, and every interaction involves mutual influence. Nothing acts alone, and nothing is purely passive. This idea is most clearly expressed in Newton's third law, but Feynman's point went beyond simply repeating the law. He wanted to change how we think about interactions. When two objects interact, they form a single physical system. However briefly, the motion that follows cannot be understood by isolating one object and treating the other as a mere background. Each object's behavior is tied to the others, and the interaction itself is the fundamental event. Consider the familiar example of a person standing on the ground. We often say the ground pushes up on the person, supporting their weight. But from the perspective of mutual influence, the person also pushes down on the ground with equal strength. The reason the person remains at rest is not because only one force is present, but because two interactions balance in a precise way. The ground and the person form a coupled system. Remove either participant, and the description collapses. Feynman emphasized that this mutuality is not optional or philosophical. It is demanded by experiment. Every time physicists measure forces carefully, they find paired effects. When a rocket expels exhaust, the exhaust pushes back on the rocket. When a magnet attracts a piece of iron, the iron also attracts the magnet. Even in cases where one object appears enormous and unaffected, such as earth and air. Falling stone. The mutual influence is still there. The stone pulls earth upward, just as strongly as earth pulls the stone downward. The difference lies not in the force, but in the resulting acceleration, which depends on mass. This realization dismantles the idea of force as something owned by a single object. Force does not belong to earth or to the stone. It belongs to the interaction between them. Feynman wanted students to internalize this shift. Once force is seen as relational, many puzzles vanish. Questions like where does the force come from lose their urgency. The force comes from the interaction itself. It does not reside in either object independently. Mutual influence also clarifies why conservation laws are so central to physics. Momentum conservation, in particular, is deeply connected to the idea that interactions are mutual. When two objects interact in isolation, the total momentum of the system remains constant. This is not because each object separately obeys a rule, but because the interaction redistributes momentum between them in equal and opposite ways. Newton's third law is, in many ways, a local expression of this broader conservation principle. Feynman often pointed out that conservation laws are more fundamental than forces. Forces can change depending on the framework or formulation, but conservation laws persist. This again suggests that force is not a primary entity, but a way of keeping track of how momentum and energy flow between interacting parts of a system. Seeing interactions as exchanges rather than as one-way actions aligns naturally with this deeper structure. The importance of mutual influence becomes even clearer in collision processes. In a collision, it is tempting to say that one object hits another and causes it to move. But careful measurement shows that both objects experience rapid changes in motion during the same brief interval. The forces involved rise and fall together. There is no meaningful sense in which one object acts first and the other responds later. The interaction is a single event, described most accurately by considering both objects together. Feynman extended this idea to microscopic physics as well. At the atomic and subatomic levels, interactions become even more symmetrical. When two charged particles interact, each alters the electromagnetic field experienced by the other. When particles scatter in a collider, the outcome depends on their mutual interaction, not on one particle unilaterally influencing the other. The language of mutual influence becomes not just helpful, but unavoidable. This way of thinking also exposes the limits of human intuition. Our everyday experience is dominated by situations where one object is much larger or more rigid than another, making its response hard to notice. A wall does not visibly recoil when you push it, but it does deform and exert unequal force back on you. Feynman liked to remind audiences that physics pays attention to effects too small for our senses, because those effects often reveal the true structure of interactions. Mutual influence also reshapes how we think about control and causation. In everyday life, we feel that we control objects by exerting force on them. Physics shows that control is always reciprocal. When you push an object, it pushes back on you. When you accelerate something, you are also accelerated, even if the effect is tiny. This reciprocity is not a limitation. It is a fundamental feature of how nature operates. Feynman's emphasis on interaction, rather than unilateral action, had important pedagogical consequences. Students who think in terms of one-way forces often struggle with complex systems, where multiple interactions occur simultaneously. By contrast, students who think in terms of interacting systems are better equipped to analyze chains of influence, feedback loops, and equilibrium states. They learn to draw boundaries around systems carefully and to account for all interactions crossing those boundaries. At a deeper level, this keynote prepares the ground for more advanced physics. In field theories, interactions are mediated by fields that respond to sources and, in turn, influence those sources. In quantum theory, interactions are described by exchanges and correlations rather than by direct pushes. The classical idea of mutual influence evolves into more abstract forms, but the core insight remains: nothing happens in isolation. Feynman's documentary-style clarity shines through in this approach. He did not romanticize interaction or dress it up in mystical language. He treated it as an experimentally grounded fact with profound implications. By insisting that every force is part of a mutual interaction, he stripped away misleading images and replaced them with a cleaner, more accurate picture of the physical world. Understanding this third keynote means learning to see motion as a shared outcome rather than as a one-sided effect. It means recognizing that the universe is woven from interactions, not from isolated actors. Objects do not simply act, they interact. Forces do not flow in one direction, they arise between things. This perspective, once adopted, changes how one sees everything from the simplest push to the most complex cosmic dance. Extending this understanding of interaction and mutual influence, Feynman pushed listeners to confront a subtle but crucial idea. Interactions are not merely events that happen between objects. They are the very fabric from which physical behavior emerges. If we remove interactions from our description, objects become meaningless abstractions drifting without context. An object's properties only reveal themselves through how it interacts with other objects. Mass shows itself through acceleration in interactions. Charge shows itself through electromagnetic influence. Even shape and rigidity matter, only because they affect how objects respond when interacting. This perspective dissolves the illusion that objects possess fully defined behaviors in isolation. A particle floating alone in empty space has position and motion, but many of its most important characteristics remain dormant until interaction occurs. It is only when another particle appears or a field is present that these properties become physically significant. Feynman emphasized that physics is not the study of isolated things, but the study of how things affect one another under well-defined conditions. One of the most powerful consequences of mutual influence is the idea of equilibrium. Equilibrium is often described as a state where forces balance, but this phrasing can still mislead if taken too literally. In equilibrium, interactions continue unabated. Forces do not disappear, they precisely counteract each other. A bridge standing still is not free from interaction. Its atoms are under enormous internal stresses, exchanging forces constantly. The appearance of rest is the result of countless mutual influences canceling out in a stable pattern. Feynman liked to draw attention to this hidden activity. What appears calm and static is often dynamically alive. A book resting on a table involves electromagnetic interactions between atoms in the book and atoms in the table, gravitational interaction between the book and Earth, and internal interactions maintaining the structure of both objects. Nothing is ever truly inactive. Stillness is not the absence of interaction, but a special balance of interaction. This idea becomes even more striking when applied to motion itself. Motion is often imagined as something object has, but from the interaction viewpoint, motion is always defined relative to something else. There is no absolute motion, only relative motion between interacting systems. Feynman stressed that this relativity is not a philosophical trick, but a physical necessity. Without interaction, there is no measurement, and without measurement, motion has no operational meaning. Mutual influence also reframes how we think about forces transmitted through intermediaries. When you push one end of a stick and the other end moves, it is tempting to imagine force traveling instantaneously along the stick. In reality, the interaction propagates through microscopic deformations and electromagnetic forces between atoms. Each atom influences its neighbors, which influence theirs, and so on. The macroscopic effect emerges from an enormous network of tiny mutual influences. Feynman found this layered picture far more satisfying than the simplistic idea of a force acting as a single, indivisible entity. This layered interaction picture becomes essential when considering time delays and finite speeds of influence. In relativity, no interaction can propagate faster than light. This means that mutual influence unfolds over time, not instantaneously. When two objects interact electromagnetically, changes in one object's motion affect the other only after a delay. Yet the interaction remains mutual and symmetrical when viewed in the correct relativistic framework. Cause and effect narratives struggle here, but relational interaction descriptions continue to function smoothly. Feynman also highlighted how mutual influence protects physics from magical thinking. If forces acted one way without reaction, energy and momentum could appear from nowhere. Mutual interaction ensures conservation. Every gain is balanced by a loss elsewhere. Every change in motion is accompanied by a corresponding change. This bookkeeping consistency is not an added rule. It is built into the structure of interaction itself. This insight becomes especially important in complex systems. In ecosystems, economies, and even social dynamics, we often see feedback loops where influence circulates rather than flows in a straight line. While these systems are not governed by simple physical laws, the intuition developed from physics, thinking in terms of mutual influence, rather than one-way causation, proves invaluable. Feynman's lessons about interaction extend beyond mechanics into a general way of analyzing interconnected systems. At the quantum level, mutual influence takes on even more surprising forms. Particles can become correlated in ways that defy classical intuition. Measurement itself becomes an interaction that changes the system being measured. There is no passive observation. The observer and the observed become part of a single interacting system. Feynman saw this not as a failure of physics, but as a deeper confirmation of the idea that interaction is fundamental. Even the concept of a free particle becomes subtle in this light. A particle may be free of external forces, but it is never free of the framework that defines its motion. It exists within space-time, obeying symmetries and conservation laws that reflect deep interactions encoded in the structure of the universe itself. Absolute isolation is an idealization, not a reality. Feynman's insistence on mutual influence also reshaped how physicists think about explanation. To explain an event is not to trace a single causal arrow, but to map a network of interactions. When a system behaves in a certain way, the explanation lies in how its parts interact with one another and with their environment. This network view avoids oversimplification and encourages careful accounting of all relevant influences. This approach also fosters responsibility in scientific thinking. When analyzing a system, one must specify what is included and what is excluded. Interactions crossing the boundary of the system must be accounted for. Neglecting an interaction is not a philosophical mistake. It is a practical approximation whose validity must be tested. Feynman valued this discipline deeply. He believed that clear thinking begins with clear definitions of what interacts with what. There's also an aesthetic dimension to this idea. Seeing the universe as a web of mutual influence reveals a kind of unity. From the smallest particle interaction to the motion of galaxies, the same principle applies. Nothing happens alone. Every event is part of a larger pattern of exchange. This unity does not come from mystical speculation, but from careful observation and mathematical consistency. As this third keynote reaches its deeper implications, it becomes clear that mutual influence is not just a rule about forces, it is a guide to understanding nature itself. It teaches us to abandon the fantasy of isolated actors and to embrace the reality of interconnected systems. It trains the mind to look for balance, symmetry, and conservation rather than for one-sided causes. In Feynman's hands, this idea becomes a powerful intellectual tool. It sharpens intuition without relying on misleading pictures. It prepares students for advanced theories where interaction is encoded in abstract mathematics rather than in simple pushes and pulls. Most importantly, it aligns our thinking with how nature actually behaves, as revealed by experiment. To grasp interaction and mutual influence in this way is to take a significant step toward the physicist's mindset. It means seeing every motion as a shared outcome, every force as a two-way relationship, and every physical event as part of an ongoing dialogue between systems. This perspective does not simplify the universe, but it makes it intelligible, replacing naive stories with a coherent, deeply connected view of reality. When Richard Feynman turned to the idea of fields, he was addressing one of the deepest shifts in the history of physics: the abandonment of action at a distance. For centuries, scientists were troubled by the notion that objects could influence one another across empty space, with no apparent intermediary. Gravity seemed to act instantly between Earth and the Moon, electricity between charges separated by air or vacuum. Even Newton himself was uneasy with this picture, describing it as philosophically unsatisfying. Feynman explained that the concept of fields emerged not to comfort philosophy, but to make physics work more coherently with experiment. A field, in the physicist's sense, is not a vague cloud or a mysterious substance. It is a way of assigning numbers to every point in space and time, numbers that tell us how objects placed there would behave. Instead of saying that one object directly pulls on another, we say that the first object alters the field around it, and the second object responds to the field at its own location. Influence becomes local. Nothing reaches out across space to grab something else. Each object interacts only with what exists where it is. Feynman emphasized how revolutionary this idea is when properly understood. With fields, space itself becomes an active participant in physics. Empty space is no longer empty in a trivial sense. It can carry structure, store energy, and transmit influence. When a charge moves, it does not instantly affect distant charges. It changes the electromagnetic field nearby, and that change propagates outward at a finite speed. This picture aligns naturally with relativity, which forbids instantaneous influence and demands that all physical effects respect the universal speed limit set by light. One of the most important consequences of field thinking is that it removes the need for hidden mechanisms. We no longer ask how one particle knows about another far away. The answer is simply that the field in between changes over time. The field is not a messenger sent from one object to another. It is a continuous, existing structure whose state evolves according to precise equations. Objects respond to the field locally, and the field responds to sources locally. The mystery of action at a distance dissolves into a well-defined dynamical system. Feynman was careful to point out that fields are not just a philosophical improvement. They are experimentally real in a very practical sense. Fields can carry energy and momentum. Electromagnetic waves transport energy through empty space, heating objects they encounter or exerting pressure. Gravitational waves ripple through space-time itself, carrying energy away from massive accelerating bodies. These are not mere mathematical conveniences. They have measurable consequences that confirm the field picture again and again. At the same time, Feynman warned against turning fields into new substances in our imagination. Just as force should not be treated as a physical thing, fields should not be imagined as material fluids filling space. A field is a mathematical description of how physical quantities vary across space and time. It earns its place not by being visualizable, but by being predictive. If the equations of the field correctly forecast experimental outcomes, then the field is doing its job, regardless of how strange it may seem. This way of thinking also unifies seemingly different phenomena. Electricity and magnetism, once thought separate, are revealed as different aspects of a single electromagnetic field. Changes in one inevitably produce changes in the other. The field framework shows that what we call electric forces and magnetic force are not independent causes, but manifestations of a deeper, unified structure. This unification would have been nearly impossible within an action at a distance picture. Feynman's treatment of fields reinforces a recurring theme in his philosophy of physics: gradual replacement of intuitive but misleading ideas with abstract but powerful ones. Action at a distance appealed to intuition because it fit everyday notions of cause and effect. Fields replace that intuition with a more subtle picture that matches reality more closely. We give up the comfort of simple stories in exchange for consistency, locality, and extraordinary predictive power. In the end, fields do not answer every why question. They do not tell us why nature is field-like rather than otherwise, but they tell us how nature behaves with astonishing accuracy. For Feynman, that was enough. The shift from action at a distance to fields was not a metaphysical triumph, but a practical one, a demonstration of how physics advances by refining its language until the equations align seamlessly with what experiments reveal. When Richard Feynman spoke about energy and momentum, he often described them as a deeper and more reliable form of bookkeeping than force. While forces change from one description to another, and can even disappear entirely in certain formulations of physics, energy and momentum endure. They are conserved quantities, and this conservation gives them a special status. Feynman emphasized that understanding physics at a fundamental level often means shifting attention away from forces and toward these conserved quantities because they reveal patterns that remain stable across vastly different situations. Energy, in particular, is one of the most misunderstood ideas in physics. People often imagine energy as a kind of substance that flows, gets used up, or disappears. Feynman rejected this picture. Energy is not a thing. It is a number we calculate from the state of a system. What makes energy remarkable is that this number stays the same, even as the system undergoes dramatic changes. A moving object can slow down, heat up, deform, or emit radiation, yet when all forms are properly accounted for, the total energy remains constant. This constancy is not explained by a mechanism, it is an observed fact, one of the most reliable facts in all of science. Momentum plays a similar role in the story of motion. It is often introduced as mass times velocity, but its importance goes far beyond this simple formula. Momentum conservation captures the essence of interaction. When objects collide or exert forces on one another, momentum is transferred, not created or destroyed. Feynman pointed out that this conservation holds even in situations where forces are complex, time-dependent, or difficult to calculate directly. By tracking momentum, physicists can bypass the messy details of forces and still make accurate predictions. This perspective changes how we think about explanation. Instead of asking which force caused a particular motion, physicists often ask how energy and momentum were redistributed. A rocket accelerates not because a mysterious force pushes it forward, but because momentum is carried away by the exhaust. A falling object speeds up not because gravity wants it to fall, but because gravitational potential energy is converted into kinetic energy. These descriptions do not deny forces. They simply place them in a supporting role, secondary to conservation principles. Feynman emphasized that conservation laws are astonishingly universal. They apply to mechanical systems, electromagnetic processes, chemical reactions, nuclear transformations, and even particle interactions at the smallest scales. The same bookkeeping rules govern a swinging pendulum and a high-energy collision in a particle accelerator. This universality suggests that energy and momentum tap into something deeper than any particular force law. They reflect symmetries of nature itself, such as the uniformity of time and space. One of the most powerful insights in modern physics is that these conservation laws are linked to symmetry. If the laws of physics do not change over time, energy is conserved. If the laws of physics are the same everywhere in space, momentum is conserved. Feynman found this connection deeply satisfying, not because it explained why the universe had these symmetries, but because it revealed a hidden order behind an enormous range of phenomena. Force-based explanations often hide this order. Energy and momentum make it explicit. This is why many advanced theories are built not around forces, but around energy functions. In Lagrangian and Hamiltonian mechanics, the central object is not force, but an energy-like quantity from which the equations of motion are derived. Forces appear only as derivatives of these functions. From this viewpoint, force is no longer a fundamental ingredient. It is a convenient shorthand for how energy changes with position or configuration. Feynman highlighted this shift as a sign of progress, not as a rejection of classical ideas, but as their refinement. The same trend continues in quantum mechanics. Particles do not follow definite paths, making the traditional force concept less intuitive. Yet energy levels, momentum states, and conservation rules remain central. Even when we cannot say exactly where a particle is or how it moves, we can still track energy and momentum with remarkable precision. This reinforces Feynman's claim that these quantities are more fundamental than force. Feynman also warned against expecting energy to provide a deeper cause than force. Energy conservation is not an explanation in the everyday sense. It is a rule that must be obeyed. It tells us what cannot happen, not why something does happen. Yet this limitation is precisely what gives it power. By ruling out impossible processes, conservation laws narrow the range of possibilities until the actual behavior of a system becomes clear. In the end, energy and momentum exemplify Feynman's broader philosophy of physics. Understanding does not come from imagining hidden mechanisms, but from recognizing patterns that hold universally. By treating energy and momentum as the deepest bookkeeping tools, physicists gain a clearer, more flexible view of nature, one that remains valid even as theories evolve and forces are reinterpreted. When Richard Feynman addressed the limits of intuition and the role of mathematics, he was confronting one of the greatest obstacles to genuine understanding in physics: the tendency to trust common sense where it no longer applies. Human intuition evolved in a narrow band of experience, moderate speeds, solid objects, familiar scales. Physics, however, explores realms far beyond this comfort zone. At very small scales, very large scales, or very high speeds, intuition often becomes not just unreliable, but actively misleading. Feynman insisted that recognizing this limitation is not a weakness, but a strength of scientific thinking. He often pointed out that people are uneasy when they cannot picture something clearly. They want a mental image that feels familiar. But nature is under no obligation to conform to the pictures that comfort us. Electrons do not behave like tiny balls, fields do not behave like elastic fluids, and forces do not behave like invisible hands. When physicists cling too tightly to intuitive images, they risk misunderstanding the phenomena they are trying to describe. Feynman encouraged a kind of intellectual courage, the willingness to let go of comforting pictures when they conflict with experiment. Mathematics enters at precisely this point. In physics, mathematics is not a decorative language used to dress up ideas already understood. It is the language in which the ideas themselves are expressed. Feynman emphasized that an equation is not just a calculation tool, it is a precise statement about how nature behaves. When intuition fails, mathematics becomes an extension of our senses, allowing us to grasp relationships that cannot be visualized directly. This does not mean that mathematics replaces understanding with blind manipulation. On the contrary, real understanding in physics often means understanding what the equations say and what they do not say. It means knowing how to use them, how to test them, and where they apply. Feynman frequently warned against mistaking the ability to compute for understanding. One must know the assumptions behind the equations and the physical situations to which they correspond. A classic example lies in the behavior of objects at high speeds. Intuition tells us that velocities should simply add, but relativity shows otherwise. Time and space themselves adjust in such a way that the speed of light remains constant. No everyday picture prepares us for this. Only mathematics reveals the consistent structure underlying these strange effects. Once the equations are accepted, the behavior becomes predictable and coherent, even if it never feels intuitive. The same lesson appears in quantum mechanics. Particles behave in ways that defy classical intuition. They can exhibit wave-like interference, exist in superpositions, and show correlations that seem impossible from a common-sense perspective. Feynman famously remarked that no one truly understands quantum mechanics in the intuitive sense. What physicists understand is how to calculate outcomes accurately. The mathematics works, and that is the measure of success. Feynman did not see this as a failure of physics. He saw it as an honest recognition of the limits of human imagination. Understanding, in science, does not require being able to visualize everything. It requires being able to predict outcomes and to recognize patterns in data. Mathematics provides a disciplined way to do this, free from the distortions of intuition. He also stressed that intuition can be retrained, but only slowly and imperfectly. Through repeated exposure to mathematical results, physicists develop a new kind of intuition, one that is guided by equations rather than by everyday experience. This mathematical intuition allows experts to make educated guesses, to see connections, and to anticipate results. But it is built on formal structure, not on naive mental pictures. Another important point Feynman made is that mathematics itself must be grounded in experiment. Equations are not accepted because they are elegant or appealing, but because they agree with observation. When mathematical predictions fail, the equations must be revised, no matter how intuitive or beautiful they seem. This keeps physics anchored to reality and prevents it from drifting into pure abstraction. Feynman's emphasis on mathematics also carried a warning against overconfidence. Equations can be manipulated correctly and still be applied incorrectly. True understanding involves knowing the domain of validity of a theory. Classical mechanics works well at ordinary scales, but fails at atomic scales. Relativity becomes essential at high speeds. Quantum mechanics dominates at small scales. Mathematics helps define these boundaries precisely. In the end, the lesson of this keynote is one of humility and discipline. Our intuitions are limited, and that is acceptable. Mathematics offers a reliable guide through unfamiliar territory, but only when used with care and tested against experiment. For Feynman, the willingness to follow the mathematics even when it leads to uncomfortable conclusions was one of the defining virtues of physics. It is this willingness that has allowed science to uncover layers of reality far beyond what common sense could ever imagine. When Richard Feynman spoke about humility before nature and the provisional character of explanation, he was expressing one of the deepest attitudes that underlies all of physics. He believed that the greatest danger to understanding is not ignorance, but the illusion of certainty. Nature is subtle, and every theory we construct is an attempt to describe patterns we observe, not a declaration of final truth. Feynman insisted that physicists must remain constantly aware that their explanations are temporary, conditional, and always open to revision. This humility begins with recognizing that our concepts are inventions. Force, field, energy, momentum, even space, and time are ideas created to organize experience. They are extraordinarily successful ideas, but they are not guaranteed to be ultimate. History shows that concepts once thought fundamental can be replaced or reinterpreted when new evidence appears. Feynman often reminded audiences that science advances not by clinging to its ideas, but by being willing to let them go. One of the clearest examples of this attitude is the transition from Newtonian physics to relativity and quantum mechanics. Newton's laws worked beautifully for centuries and still work within their proper domain. Yet they were not the final word. When experiments revealed phenomena they could not explain, new frameworks emerged. Relativity reshaped our understanding of space, time, and gravity. Quantum mechanics overturned classical notions of determinism and locality. These revolutions did not render earlier physics worthless, they showed its limits. For Feynman, this was not a failure of science, but its greatest strength. Humility also shapes how physicists interpret success. When a theory makes accurate predictions, it is tempting to believe that it reveals reality exactly as it is. Feynman warned against this temptation. A theory can be extraordinarily successful and still incomplete. Its success tells us that it captures some real regularities in nature, not that it provides a final picture. Confusing predictive power with ultimate truth leads to dogmatism, which is fatal to scientific progress. This attitude has practical consequences for how science is done. Physicists are trained to doubt even their most trusted theories when new evidence appears. An experiment that contradicts theory is not dismissed lightly. It is examined carefully. If the contradiction holds, the theory must be revised or replaced. No authority, tradition, or reputation can protect a theory from this process. Feynman valued this ruthless honesty above all else. He believed it was the ethical core of science. Humility before nature also affects how explanations are framed. Feynman resisted the idea that science provides deep why answers in the philosophical sense. Instead, it provides increasingly accurate how descriptions. When we ask why gravity exists or why the laws of physics have the form they do, physics eventually reaches a point where it can only say, this is how nature behaves as far as we can tell. Demanding more than this is demanding something science is not designed to deliver. This acceptance of limits is not a resignation, it is a liberation. By acknowledging what we do not know, we keep open the possibility of discovering something new. Every unanswered question becomes an invitation rather than a failure. Feynman often spoke with delight about the mystery that remains at the heart of physics. For him, uncertainty was not an embarrassment but a source of wonder. The provisional nature of explanations also encourages creativity. If theories are not final, then new ideas are always possible. Physicists are free to explore alternative formulations, new mathematical structures, and unconventional approaches. Many of the greatest advances in physics came from individuals willing to question accepted explanations and to imagine radically different ones. This creative freedom depends on humility, the recognition that current understanding may be improved. Feynman also emphasized that humility protects science from ideology. When theories are treated as unquestionable truths, they can become tools of authority rather than instruments of discovery. By contrast, a culture that values provisional explanations remains open, self-correcting, and resilient. Disagreement is not a threat, but a driving force. Competing ideas are tested by experiment, and the ones that survive earn their place through evidence alone. This attitude extends beyond professional physics into a general way of thinking. Feynman believed that the scientific mindset curiosity combined with humility was valuable in all areas of life. Being willing to say, I don't know, is the beginning of learning. Being willing to change one's mind in light of new evidence is a sign of strength, not weakness. In the end, the seventh keynote completes the picture of understanding force and physics the way Feynman did. It reminds us that all our explanations, no matter how elegant or successful, are provisional maps of reality, not reality itself. Their purpose is not to end inquiry, but to guide it. Humility before nature keeps science alive, honest, and endlessly fascinating. It allows us to celebrate what we have learned while remaining open to what we have yet to discover, which, for Feynman, was the true joy of physics.